Very interesting paper to think about. They do some interesting things and obviously have a sort of a bold conclusion. They don't go fully out on the limb. The title has a question mark at the end of it, but it's they throw it out there that maybe this answer is a very important, maybe the most important question in empirical asset pricing. Is it characteristics or covariances? So what they do is to use a random forest to estimate conditional expected returns, which is a standard thing to do now. Random forests and neural networks seem to predict returns pretty well, and random forests are much faster to train, so this seems like a very sensible thing to do. And then they construct these factors in a hedged portfolio and find that the hedged portfolio has a very large Sharpe ratio. And if the hedged portfolio, as Alejandro said, were truly hedged against factor risk, then this would seem to violate rational pricing and suggest that it must be covariances and characteristics and not covariances that are driving risk premium. But we know that the big issue in this whole area is it characteristics or covariances, is that we estimate covariances with error, right? And if covariances are estimated with error and characteristics are correlated with true covariances, then there's room for characteristics to explain returns. So betas are estimated with error. This thing is very fast. I have the same, there we go. So I'm going to spend a chunk of my time talking about, this issue's everywhere, right? It's endemic, it's unavoidable. It's always there when we're talking about characteristics versus covariances. So I'm going to spend a chunk of my time explaining where it shows up in this work, and then I'll spend the rest of my time trying to give some sense of quantitatively, can the errors in beta estimation and covariance estimation explain the quantitative results that they're finding. So what I'm going to do is I'm going to give you a very simple example to explain the way that the estimation errors in betas affect the results of the paper. It's a very simple example. It may be too elementary for this group, but I think it's important to fix the ideas and to help interpret the simulations, which otherwise would be something of a black box. And I'm going to review the paper's methodology for a few minutes before I explain the simulation, and I'll have a few other comments at the end. So here's my very, very simple example. I have three assets. It's a CAPM economy, so all the risk premium is going to be in one asset, that's the market. And I'm going to pull the distributions of these asset returns from historical returns on the market and from the residuals of the regressions of two factors on the market. So I'm taking the residuals and not the alphas. And so there's zero mean, zero beta assets. And so all the risk premium in this economy is carried by the market asset. And the true betas of these three assets with respect to the true factor of the market are obviously 1, 0, and 0. And their true means from the data are as given there. And what I'm going to do is I'm going to put a little bit of beta estimation error in and then see what we get out of the paper's methodology for the hedging portfolio and see what its Sharpe ratio is. We're going to have a little bit of beta estimation error, plus or minus 0.1. And just a tiny bit of mean estimation error. I know the true means of these assets, the market mean and the zero for the other two assets, but I'm going to add 1/10 of a basis point plus or minus estimation error on the means and see how the estimation error affects the results. So the hedge portfolio in the paper's construction is defined by being zero weight and orthogonal to the vector of betas, and loading on the vector of projected expected returns that they get from the random forest. So that's a characteristic. In this example, it's going to be M, that's my characteristic. Those are the estimated means. The true means plus or minus 1/10 of a basis point. Now, they construct their hedge portfolios normally by minimizing the sum of squares, but I just have three assets and three constraints, so we just solve the constraints to find the hedge portfolio. And as in the paper, I'm going to rescale the weight so that the long and short side sum to 1, so we can interpret them as long-short portfolios. So here's a little example, putting some numbers in it. So my estimated betas are 0.9, 0.1, and minus 0.1. So each one has a little bit of estimation error. And my mean estimates are off by 1/10 of a basis point, plus or minus. As you do this calculation, here's the hedge portfolio that you get. Now the hedge portfolio, if it were orthogonal to the true betas, couldn't load on the market. because the other two assets have zero betas and can't compensate for any market loading. So if I had the true betas, the hedge portfolio would have a beta of 0, and it would have a 0 risk premium. But I got a little bit of estimation error, and I'm asking the hedge portfolio to load on the characteristic which is correlated with the true betas. The true means with a little bit of estimation error, correlated with the true betas. And so this asking the portfolio to load on the characteristic causes it to load on the true factor, on the market in this case, which it can do because of the estimation errors in the betas. And so we're going to get a loading on the market anytime we have beta estimation errors. And this particular portfolio, given the distribution of these assets, has a Sharpe ratio of 11.7%. That's a small Sharpe ratio. It's not nearly as big as in the paper, but this is a very small example. Now, this is a problem that we all know. It's just errors and variables bias. So the hedge portfolio, the return of the hedge portfolio, is just the Fama-Macbeth regression coefficient when you regress returns on betas and estimated betas and the characteristics. So this, as Alejandro said, goes back to Fama. In fact, before Fama's book, Bar Rosenberg wrote a paper in JFQA that explains the constructions of these portfolios as the portfolios that underlie Fama-Macbeth regression coefficients. And the Fama-Macbeth coefficient in this cross-sectional regression, the cross-section is the three assets that I have. In this cross-sectional regression, the Fama-Macbeth coefficient has a positive mean because of the errors, the OLS errors and variables bias. We've got estimated things on the right-hand side of the regression, and the errors in those are going to lead to biases in the regression coefficients. And the positive risk premium of the hedge portfolio is exactly the errors and variables bias from OLS applied to the Fama-Macbeth regression. Okay, so you might ask, how much did I cherry pick this particular numerical example to get, oh, I'm supposed to point this way. I keep pointing, right. It doesn't work to point at the screen. You might ask how much I cherry picked this example to get the positive risk premium and the positive Sharpe ratio. And I did cherry pick just a little bit, but let me show you how much I cherry picked. Let's think about all of the examples of this sort that I could generate, where I go plus or minus 0.1 on the beta estimation error and plus or minus 1/10 of a basis point on the mean estimation error. There are 64 different combinations, 64 different examples that I could have generated. You can think of this as the population of possible samples I could have drawn in my estimation. And the Sharpe ratios of the hedge portfolios in those 64 cases are never negative. I gave you an example that's here, so I cherry-picked a little bit, but they're never negative, and they're half the time positive. And the beta estimates in this population are unbiased. I did plus or minus 0.1 each time. And the mean estimates are unbiased. I did plus or minus 1/10 of a basis point each time. So I have unbiased estimates, but I feed them in. The errors and variables bias is going to cause the Sharpe ratio to have a positive bias, okay? So in this little example, we get a positive risk premium for the hedge portfolio because of the errors and variables bias. So what I want to do the rest of the time is I'm going to show you the results of a simulation to get some sense as to how important this might be in the data. But first, let me review the methodology just a little bit so that to build on what Alejandro did in explaining the paper. Okay, so they estimate betas through this singular value decomposition. They use one-year panels of daily data. So they have 252 days, and a T by N return matrix where T is 252 and N is the number of stocks. And they extract the eigenvectors using singular value decomposition to get 252 eigenvectors. And we could think of those as month 12 betas. So what we would normally do, I think, is we would take these month 12 betas and we would use them for month 13. We use a rolling past window to estimate betas and then use them for the subsequent month. But that's not exactly what they do. They instead add another step, which is this rolling panel regression. So let me explain that. So I've set it up for a 5-year rolling panel. Alejandro said it was 3 years. Alejandro and Nick told me by email it was 5 years. It doesn't say in the paper, but it doesn't make any difference. But this is a 5-year rolling panel. So we have estimated betas in month 12 through the first 252 days, and we're going to use those in the next 12 so that we have 12 total months as lags. On the left-hand side of the panel regression, we're going to put the month 24 betas, and we'll do that each month for the whole panel of stocks until we have a 36-month panel. And we'll get the regression coefficients, and we'll use the last 12 estimated betas to forecast month 84 estimated betas. I think that's the process, right? Okay. And I don't know how much this adds to the paper as opposed to just using the last 12 months to use for month 13 betas, but it's kind of an interesting feature. Okay. Did I skip something? Oh, yeah. So the factor construction, which Alejandro already explained and I mentioned already. These are Fama Macbeth portfolios. My understanding is in the industry they're called Barra factors because this is the way Barra constructed factors to do return attribution analysis. Of course, Bar Rosenberg should get credit as well as Fama, as I mentioned, for this methodology. All right, so I'm going to do a simulation. So I'm going to simulate a 6-factor model for daily returns. So I'm going to do 3,000 stocks, daily returns for 50 years. Calibrated, my 6 factors will be the Fama-French-Carhart factors. In each simulation, each of the 3,000 stocks is going to have constant betas over time. And I generate the 6 betas for each stock by drawing from a distribution calibrated to the cross-sectional distribution of betas. I add independent homoscedastic idiosyncratic shocks to the factor part of the return for each of the 3,000 stocks. I use the singular value decomposition to get betas at the end of each month. I do the 60-month panel regressions on 12 lags to forecast betas. I construct the factors, the hedged and the unhedged portfolios as in the paper. And then I repeat this 10 times so I get some idea of the distribution of outcomes that we might anticipate. And here's the sort of main result. Hedge is the unhedged portfolio. H is the hedged portfolio. Use the unhedged portfolio. I get an annual mean return for the hedged portfolio around 6%. The paper gets 8.5. Okay, that'd be fine. The paper gets 8.5, so it's a little bit low. My unhedged portfolio does a lot better than in terms of mean return than in the paper. But the main thing is the Sharpe ratios. So the Sharpe ratios are between 110 and 130% typically in this simulation for the hedged portfolio, compared to the 150% in the paper. And this is purely errors and variables bias that's driving this. The hedged portfolio is orthogonal to the estimated betas, but it's not orthogonal to the true betas, and because you're forcing it to load on the expected returns, it's loading on the true betas. So how does it load on the true factors? I need to, I guess, speed up just a little bit. The hedged portfolio actually does load on these principal component factors. So 70% or so of its variation is actually explained by the PC factors, even though it's orthogonal to the estimated betas. So when I do a regression in time series on the constructed factors, the hedged portfolio does load on them. The other reason that the hedged portfolio loads on the true factors is that the PC factors don't quite span the true factors in the simulation. So in the paper, the PC factors explain about 50% of the variation of stock returns. That leaves room for some unspanned true factors, and that's what I see in the simulation. 60 to 80% or so of the variation in the true factors. These are the true factors projected onto the assets, so these are the true traded factors. they're not fully spanned by the PC factors. The hedged and unhedged, the hedged portfolio has an alpha relative to the PC factors. So even though this is an APT economy by construction, the hedged portfolio has an alpha. The PC factors are not the true factors. And it's statistically significant in most of the simulations. Also, the Gibbons-Ross-Schenken test with the traded factors as a test asset rejects the PC factor model. This is 50-factor PC factor model. We've got a lot of factors, but it's rejected as explaining the risk premium in the economy when I use the true traded factors as the test assets. So let me conclude with a couple of other comments. So first, there's a little bit of a literature in statistics on this singular value decomposition with panels that have more assets than time periods, which is the situation here. And that's the reason we're using it instead of estimating the covariance matrix. So here's a nice short survey paper. And the sort of the point of this paper is that the eigenvalues in this setting, when you have more stocks than time periods, the eigenvalues are biased upwards. So this is an important point. It appears in the data that the first 50 factors explain about 50% of the variation in stock returns, but that's apparently a biased estimate. And so your PC factors may be explaining less of the variation than you think. This paper in Economics Letters is a paper about this exact issue applied to the APT. So that's something that you should investigate. So I will say that my simulation doesn't explain everything that they find in the paper. And in the simulation, the PC factors do carry risk premium. It is surprising to me that in the data, these PC factors seem to carry very little risk premium. I'm not so surprised that the hedge portfolio has a risk premium because of the beta estimation error. But I am a little surprised that the PC factors don't carry risk premium. So I think that's a very interesting observation. Now, the paper only tells us about the Sharpe ratios of the first 5 factors. I'm not sure why that's the case. What I would do is I would plot the squared Sharpe ratio of the first n factors for all of the factors. Give me a plot from 1 to 50 if you're using 50 factors. I mean, you don't have to square them, but if you square Sharpe ratios, they add up across independent factors, so it's a natural thing to look at. Are there really no risk premium in these factors? The first 5, there aren't, but is it true that there aren't any risk premium in the factors? I also think you should report the alpha. I don't think it's in the paper, I don't think it was in the presentation, of the hedge portfolio on your PC factors. If it's 0, the story goes away. The risk premium of the hedge portfolio is just beta estimation error. There is nothing to explain. The PC factors explain the hedge portfolio. I don't think it's going to be 0. I think it's significant, but I think you should report it. You should also tell us what the R squared is. How much of the hedge portfolio variation is explained by the PC factors. I think those will be interesting things to add to the paper.